Hello, we're going to talk about our last chapter on quantum mechanics, which is talking about bonding, so talking about molecules. Let me share my notes. So I'll be going back and forth more between the figures in the text and my notes because the figures are very good. They help you understand it a lot better than words. So we'll start talking about the bond, and it'll be very similar to Gen Chem. We'll look at valence bond theory and then molecular orbital theory and see when they're each useful. Molecular orbital theory, it's used in all of the modern computational work that you may have done without really knowing how the codes work. So we'll talk a lot about that, and we'll practice some of it too using the Gaussian software. So start out with remind yourself, probably you use valence bond theory most in organic, and it's based on quantum mechanics, but it's based on doing the quantum mechanical solutions for atoms and then seeing how you could use those atomic orbitals to think about bonding. So read the Chemist Toolkit 25 and 26. That'll remind you of Lewis structures and VSEPR geometries. And then we can kind of compare back to that. So Lewis structures and VSEPR geometries, that was a theory created by Lewis way before quantum mechanics was developed. And so our valence bond goes beyond that. So with the development of quantum mechanics, you can see where Lewis structures and VSEPR geometries come from, but they're not very quantitative. So important thing to remember is that all of these theories in general for molecules are going to use one approximation. So when you say that you can solve Schrödinger's equation exactly, the only molecule you can solve it for is H2 plus. So that's diatomic hydrogen with one less electron. So you only have one electron to worry about. And when you say you can solve it exactly, you can only solve it exactly if you use the Born-Oppenheimer approximation. So it's not really an exact solution. So what the Born-Oppenheimer approximation takes advantage, and it was created in 1927, so right after the development of quantum mechanics, and it pretty much is used in all of the big software packages. My research since the last time I went to Oak Ridge, which was in 2015, has been on looking at when the Born-Oppenheimer approximation fails, and it makes the calculations just crazy complex, but in some situations it's important to not use that approximation, but in general it's valid. So the approximation basically says that a proton and a neutron are about 2,000 times the mass of an electron. So for any nucleus you have with many protons and neutrons in it, it's going to be so much heavier than an electron and going so much slower that you can solve Schrödinger's equation by setting the positions of the nuclei and then solving Schrödinger's equation for the electrons and then resetting the positions and solving again. And what you get out of that, let's take a quick look at the figures. So what you get is something that looks like this. So this is a molecular potential energy curve. So it shows you why a bond forms. So on the x-axis is the distance between two nuclei. So if we're talking about a diatomic, so you would set that internuclear distance, solve Schrödinger's equation for the electron, get an energy, and that energy would be someplace on this red line, depending on where your R is. And you do that over and over. That's called optimizing the geometry. And so you discover that the best geometry is at the bottom of this well. It's the most stable when the potential energy is the lowest. And so let's go back to my notes. Okay, so now if we continue thinking about that idea, valence bond theory for diatomic molecules. valence bond theory says that a bond is formed when an electron in an atomic orbital on one atom pairs its spin with that of an electron in an atomic orbital on another atom. So you remember that idea. You're looking for orbitals on two atoms, each with only one electron. And then as you push them together, you get overlap and a high probability of finding the electrons between the nuclei, which essentially serves as glue to hold them together. And so, let's see if there's we don't need to look at a diagram. So if we want to think about the bonding, for example, in the H2 molecule, each of the 1s orbitals on each of the hydrogens is unpaired. So if you push that together, decrease the R value to get an optimal value, you'll create a sigma bond, and you'll create a area between the two nuclei where you have a high probability of finding electrons. So high probability of finding that negative charge that will attract both of the nuclei and hold it together. So valence bond theory is really taking advantage of this idea of the orbital approximation. So for the wave function for the hydrogen molecule, so on the left-hand side, it's going to be a wave function for 2 electrons. But we're going to assume is that you can put an electron on the A nuclei. So let's say this is A and another one on B. But because that wouldn't look any different than having the second electron on A and the first one on B, you have to include both of those. But what you're approximating is that this orbital, which is a function of the coordinates of both electrons, can be approximated by individual functions multiplied by each other that are only a function of the coordinates of one electron. So a valence bond wave function you get from the orbital approximation, and you can use Schrodinger's equation to calculate the energy of this wave function with different values of R and get the potential energy curve. So that's a process that would take a lot of time. Usually you'd use a computer. Page 393. Yeah, on page 393, figure 3 at the bottom. I'll go quickly there. Yeah, this just shows you that when those two wave functions are overlapping, you're getting constructive interference between the nuclei. And so you're getting a higher probability of finding the electrons in that region versus outside the nuclei. So that's why a bond is forming. So this is a description of the valence bond theory explaining the bonding in diatomic nitrogen. So diatomic nitrogen would have a single sigma bond. So if you look at the electron configuration, you have 3 electrons, 1 in each of the p orbitals. So the p orbitals that are along the bond axis can overlap, and you'll get a sigma bond. And then you can also have the overlap of the perpendicular p orbitals sideways, and those would then give you 2 more bonds, and those are pi bonds. So I think that valence bond is fairly familiar, I hope. So when you're doing this and you're thinking about the orbital approximation and doing a geometry optimization, you have to realize that if they're closer together, you have more overlap of the electrons or of the electron density function, and so more electrons between the nuclei. But if you get the nuclei too close together, then they're going to start to repel each other. So the charge on one nuclei times the charge on the other times the fundamental charge over 4 pi epsilon 0 r. So that's just the Coulombic potential that we used for the attraction of a proton or something positive to an electron. But now we're looking at how it also can explain the interaction of 2 positive particles. And so that's why, as it gets closer together, you get a minimum, and then it starts going back up, and it isn't favorable, and that's because you're getting this nuclear repulsion. So we looked at the bonding in nitrogen in that figure. And explaining it with valence bond theory is talking about what are the atomic orbitals that overlap. So we talked about the PZ, those are the ones along the bond axis overlapping to form a sigma bond, and then the PX and the PY, which are perpendicular to that, can overlap sideways to make pi bonds. So stop and do self-test 9A.1, where you do the same thing, but you do it with diatomic oxygen. When we're talking about polyatomic molecules, you can do exactly the same thing. And so stop and do self-test 9A.2, where you look at using valence bond theory and what orbitals would overlap to make the NH3, the ammonia molecule. And so after you've done that problem, you'll notice there are two errors that are common in valence bond theory. The number one is the number of bonds you can have. So we'll see in a second, if we try to explain the bonding in methane, we'll get the wrong number of bonds. And then also the geometry. So from the self-test 9.8.2, you can see that the bond angle is not what it should be from our understanding of VSEPR, at least, using valence bond. And so those two errors lead to needing a deeper theory for valence bond. And so what we're going to do is we're going to add two ideas to it. So when you start and you think about methane on the left-hand side of this set of notes, the electron configuration of the carbon is a 2s2, 2p2. So the valence electron configuration, the electrons that contribute to bonding. And so when you look at that, you'd see that there are only two orbitals on carbon that can overlap with other atomic orbitals on other atoms. And so that would predict that you can only have two bonds to a carbon atom. But we know that carbon most commonly has four. And so we have to be able to explain that. So we're going to add two ideas: promotion and hybridization. So these are concepts that you saw all the way back in Chem 107, and then you used them a lot in organics. So hopefully this is somewhat of a review. So the idea of promotion is that we could take one of the electrons in the s orbital and promote it up to a p orbital. That would give us four orbitals, each with one electron. So that solves the error of not the right number of bonds being predicted. That takes a little bit of energy, but as you saw, when you form a bond, the system goes way down in energy on that potential energy curve. And so you get that energy back. The other thing is you don't want to think about this as actually happening, like the electron gets promoted and then the orbitals are mixed. Instead, you want to think about it as a way to explain what we understand about the bonding around carbon. So now we want to think about the geometry. So if we just did the promotion, you'd have an s orbital and three p orbitals forming bonds. And you look at the p orbitals, you know for sure they're 90 degrees from each other. So three of the bonds to the carbon would be 90 degrees with each other. And we know that the bond angles in methane are 109.5. So we know that's not right. So we have to do more than promotion. So promotion solved the problem of not the right number of bonds, but it hasn't solved the problem of not the right geometry. So what we're going to do is we're going to mix them. So we're literally going to take these functions and we're going to add them together mathematically. And when you do that, if the Hamiltonian, so if you're solving Schrodinger's equation and using the S function, because that is a solution we know, then you'd get back energy of the S times the S function, and the same thing with P. And so if you did a sum of the two, you'd also get back a constant times the functions. And so a linear combination of functions that are solutions to Schrodinger's equation can also be solutions to Schrodinger's equation. And so when we look at the hybrid orbitals, the sp3 hybrid orbitals, there are going to be four of them, H1, 2, 3, and 4. The first one is all the functions added. Second one is some added, some subtracted. And so in different combinations, and you'll see that this allows for the functions to be orthonormal. And we'll look at that in some of your homework. And so when we look at sp2 and sp, you get the same exact kind of argument. So you can look at those. Your book gives you the functions. So the sum of the p's and s's that make sp2s and sp hybrid orbitals, but it's the same idea. We had to hybridize them to explain the geometry and the number of bonds in whatever system that we're looking at. Okay, so the hybridization of any number of atomic orbitals always forms the same number of hybrid orbitals. So sp3 are 1 part s, 3 part p, and you're always going to get the same number. So that means you're going to get 4 hybrid orbitals. sp2, you're going to get 3, and sp, you're going to get 2. So stop and do self-test 9A.3, where you describe the bonding in phosphorus pentachloride. And there are other hybrid orbitals in the table right below it, because we know that sp3, sp2, and sp aren't going to be used for this one because we have 5 bonds. So you'll have to use that table. Read example. Test. Okay, yeah, so work through the example and understand 9A.1, and then right after that, there's a test of whether or not you understood it, self-test A.4. Okay, so now we want to think about the idea of resonance. So the idea that you can draw more than one structure and that they contribute to the true structure of the molecule. So something like HCl. So we're going to think about this covalent versus ionic resonance structure. So if we want to think about the bonding in HCl, we have to describe the wave function as a function of the coordinates of both electrons that are in that bond. And so if it's purely covalent, you would have the electron on the hydrogen, electron number 1, electron number 2 on the chlorine, and then electron number 2 on the hydrogen, electron number 1 on the chlorine. So this would be your orbital approximation. You're approximating this function that's a function of the coordinates of both electrons to be products of functions that are coordinates, are functions of coordinates of just the individual electrons. So that would be purely covalent. But we know HCl is a polar molecule. And so the other wave function that you need to think about is the fact that the electron can be more on one side or the other. So if we're talking about it as purely ionic, H plus and Cl minus, then you would have both of the electrons on chlorine and none of the electrons on hydrogen. So your wave function would be a product of electron number 1 on chlorine and electron number 2 on chlorine. That would be ionic. And so you're going to write the wave function for the molecule as a sum of the covalent plus the ionic. And so it's a blend of those two. And you can use something called variational theorem, which we'll talk about a little bit more at the end of this chapter, to find the value of lambda and to figure out really how much ionic character is there. So the variational theorem says that any function that you're using as a trial, you can make it better if you lower the energy somehow. So in this case, if we lower the energy of the system by varying this lambda, then that means we can get the value for lambda that gives us the lowest energy. Therefore, it tells us how much ionic character this molecule has in its bond. And so because the wave function squared is the probability, that means that the lambda squared gives you the probability of the ionic nature. So gives you the proportion of the ionic nature. Self-test 9A.5. Stop and work that one. And then we'll just wrap it up with some of the most important aspects of valence bond theory. So we get the names and types of bonds being sigma and pi. You get the idea of promotion and hybridization to correct the fact that you often don't get the right geometry or the number of bonds. And then this idea of resonance. We looked at it here explicitly for the ionic nature, which is the same thing as saying the the polar nature of the bond. You can also just look at it in reference to something like benzene. You can look at how the orbitals have to be added together to get different resonance structures for different molecules that aren't just covalent and ionic in nature. So, I think I will keep going. Of course, you can always take a break if you want to. A lot of molecular orbital theory we're going to do as a lab in class. So we'll just look at some of the huge differences in the nature of the calculations versus valence bond theory. So molecular orbital theory will start with the simplest system, homonuclear diatomic. So H2O2, N2, anything with the same atoms and only two of them. We're going to use the Bohr-Oppenheimer approximation. And we're going to use H2 plus, the simplest molecule, because it has exact solutions. And just like we use the hydrogen solutions as wave functions for many electron atoms, we can do the same thing. We can use the orbitals we get for H2 plus and use those and just put more electrons into them for things like N2 or other larger molecules. So all modern work builds by formulation of models based on linear combination of the atomic orbitals on the atoms in the molecule. And that makes it sound like valence bond theory, but it's not. So you're not taking the orbitals solved from the atomic Schrodinger's equation and seeing how they overlap. Instead, you're using those orbitals as approximations to a function, and then you're using variational theorem to look at how you can minimize the energy by varying parameters in them. So really this part about you use linear combinations, that's as a first approximation to what the wave function should look like for a molecule. And that's kind of vague, but it's a very subtle distinction between valence bond and molecular orbital theory. So if we're looking at H2 plus, we have two protons, we'll call them A and B, and one electron. And so it's going to make sense if you need to find a function for the electrons in this, for the electron in this system. We know that a function on each of the orbitals of S shape can be added together, and that's probably the lowest energy situation. So when you add it together, you can vary other parameters besides C and A and CB. There are parameters within the wave function you could also vary. And if you take 367, we'll actually do this calculation ourselves and see what that means. If it's homonuclear, though, the C's have to be the same. And so the square of each of those is giving you the probability that the electron is in each of those orbitals. And those two have to add up to 1, but they also have to be the same. And so CA has to be equal to plus or minus CB, because when you square them, the minus will go away. And so the wave function equals psi A plus or minus psi B. That's because this can be plus or minus the C's relative to each other. So the bond is a result of the overlap integral. So when you do this calculus, we're going to do it all on a computer, so don't worry too much about it. But understanding some of the complexities of what the computer is doing is important. So the overlap integral is how much each of the wave functions multiplied by each other essentially overlap. And that makes sense because it's that overlap of the orbitals on the two atoms that gives you that high probability of finding the electrons between them and therefore creating a bond. So go ahead and do 9b.1, where you actually have to calculate the overlap integral for the hydrogen molecule. So when we look at this linear combination, if it's the psi A plus psi B, so the s orbital on the two atoms added together, it's going to be lower in energy, and you're going to get a bonding orbital. And if you have the subtraction, so psi A minus psi B as your wave function, it's going to be anti-bonding. if you think about it, it's because the orbital on A has a positive sign, and now if you put a negative there, psi B has a negative value. And so as you push them together, you're getting destructive interference between the nuclei because the positive on A is canceling with the negative on B. And so you're getting less probability of finding the electrons between the nuclei, which gives you a nodal plane. It actually gives you a position between the nuclei where there's zero probability, and that helps to pull apart the nuclei and therefore helps to decrease the strength of the bond. So if we're thinking about bonds and their order, or what you can learn from molecular orbital theory, if you have the molecular orbital diagram, so you have a sigma bond and a sigma star. The sigma bond is the bonding, sigma star is the anti-bonding. When we look at hydrogen, if we put its electrons into this picture, diatomic hydrogen has 2 electrons, so they'll both go into the 1s. And that means that they both go into bonding orbitals. So if you calculate the bond strength, you have n equals 2, n star equals 0. There are no electrons in the antibonding. Times 1/2 tells you that the hydrogen molecule has a bond order of 1. But if you do the same thing with helium, helium has 4 electrons. Each helium atom contributes 2. And so you have 2 in the 1 sigma and 2 in the 1 sigma star. And they essentially cancel each other. So 2 minus 2 gives you 0, and the bond order is 0. So helium doesn't form a molecule like H2 does because the bond order would be 0. So stop and do self-test 9.2 or B.2. And it's looking at the lithium hydrogen molecule and whether or not it would exist in the same kind of way by looking at its bond order. So we're going to do a molecular orbital activity in class for homonuclear diatomics. And then for section 9C, where you go to heteronuclear, and now you just have to think about the contribution. The Ca and the Cb aren't the same because you're going to have an asymmetric molecule. So read this part over for the concepts. We won't do any of this math by hand. We'll only do it on the computer using some software called Gaussian. And then 9D topic we'll talk about in class. And you don't have to read that in class. So we're going to talk about polyatomic molecules, a little bit about Huckel theory. So let's just go to molecular diagrams. I do want you to read, though, the computational chemistry bit where it talks about how the calculations are done. So it's the very last 9D.4 in the D topic. We'll go into this when we're doing calculations. We'll talk about things like self-consistent field and Gaussian type orbitals, and we'll talk about ab initio versus empirical methods. So you don't need to read the rest of that topic, but please do read that very last section. That'll help as we work through our activity in class. So that is all for 9. We have one more section this week, and that's just looking at the general properties of spectroscopy.